Well, hello everybody, Dave here, and this is our first lesson on a series of lessons dealing with the ChiSquared test. Hopefully you've dealt with significance testing in previous lessons, specifically one proportion, one mean, two proportions, and two means. This is another test that you can use when we have multiple proportions that we want to check simultaneously. We've seen in the past that if we have a single proportion, we can actually use a one proportion test to determine the significance of that value's difference from the expected value of the population proportion. But what if we have a number of proportions and we want to check if our resulting observations have proportions that match up to the point where it is a good fit for that particular distribution? When we're dealing with something like that, we have to shift to a chi-squared scenario. You could technically do a one proportion test for all of the different proportions, but that would take a whole lot of time and effort to do so. Instead, with the chi-squared, what we can do is we can simultaneously check all of our proportions to all of the expected proportions and determine whether there is a difference or not, and whether that would be significant. Moving forward in the lessons, we'll actually talk about two other types of chi-squared tests that are going to be important, specifically the test of homogeneity and the test for independence. So if we want to see if we have multiple populations of data and if those differences are significant or not, we're going to use the chi-squared test for homogeneity. If we want to see if there is an independence of two populations or not, we're going to deal with that chi-squared test for independence. So this lesson is going to focus specifically on the goodness of fit, and subsequent lessons are going to deal with the other two. So the classic chi-squared test that is done in class is dealing with the proportion of the different colors of M&Ms that exist in a given bag. And the idea behind this is that we know what the actual manufacturer expects the proportions to be, and then when we actually get our own bag of M&Ms and we open it up and we count them, do those proportions match up with the expected proportions given to us by the manufacturer? So you can see here that we have a one-way table to describe the color of the M&Ms and the number that existed. So we see that we had a bag of 60 M&Ms, and from that the number of blue M&Ms was 9. So our observed proportion for the blue M&Ms is 0.15. I also want to point out the fact that when we're dealing with a goodness of fit test, we are almost going to exclusively use a one-way table. If you're dealing with chi-squared and you see a two-way table, that's going to point to the other types of tests that we're going to talk about in a future lesson. So this table right here is a pretty good indication that we're going to go ahead and use the chi-squared goodness of fit test. So let's imagine that we didn't know about the chi-squared and we were just going to do a one prop test like we've learned in previous lessons. If that's the case, our null hypothesis would be that the proportion is equal to 0.24 in the case of blue, and the alternate hypothesis is that it's not equal to 0.24. We don't know which way it's supposed to go, but in those cases we're going to deal with a two-sided test, which means it's just not equal. Now, recognize that if we had to do this for every single color, we would have to do 6 significance tests of one proportion each, which could take a lot of time and effort. You'll notice again, though, that with our state, we still stated this in context of the problem. So regardless of the significance test that we use, this is still going to be a case. Obviously, this is going to be highly inefficient. We're going to want to come up with another way, but this would be the way you'd set it up if we had to do each proportion individually. What the chi-squared goodness of fit test does is pretty straightforward. The null hypothesis now is going to be that the proportions are correct. The alternate hypothesis would then be at least one of the proportions is not correct. The key idea here is that it's not a number of proportions that has to be not correct. It could be one, it could be all. But the point is, if we see some statistical difference between the proportion that they give us and the proportion that we observed, at that case, we are going to reject the null hypothesis. So a difference between chi-squared testing and other significance testing is instead of having quantities here, we are actually going to write out these statements. What some people do like to do is physically write down that P blue is equal to 0.24 and actually list off all of the equal and not equal statements. If you want to go that route, that's fine, but statistically, these statements are completely okay. So as I mentioned, this would be the other way that you could state the hypotheses, that we have the null where they're all equal versus the alternate where at least one is not. Now, the key idea behind this is, of course, the subscripts on these parameters to make sure that we are aware that we're talking about the proportion of blue, the proportion of orange, not just P. So make sure that you state these very clearly if you're going to do that. Now, the first thing we have to do is we're going to compare the observed counts to the expected counts that we should get from the factory. And because of this, we actually have to do a calculation of this expected count. They are not typically given to you in a question. The expected proportions are given, but the resulting expected count as a result of those proportions is something you're going to have to calculate. But when you do that, it's a fairly straightforward calculation. If we expected 0.24 as a proportion of blue and we had a bag of 60 M&Ms, then 0.24 times 60 is 14.4. So on average, we would expect 14.4 blue M&Ms. Now, realism is something that you may want to consider here, because you're thinking, well, hold on, there's not 0.4 blue M&Ms in a bag. Well, you're true, but in this case, because we're dealing with expected values, we don't want to round these and we don't want to impose realism on the expected. Observed obviously is observed. It's either one blue M&M or it's not. But when it's expected, again, we're talking about this in terms of the average amount that should exist in all bags of 60 M&Ms. So you're going to write these to about 2 decimal places is the way to go. So you can see here that I've written down the calculation for all the different colors. I would advise you that if you're dealing with any sort of assessments or questions, that you show these calculations, because that indicates to the person who's going to be assessing your work that, okay, this person understood that the expected value is something that they have to calculate directly. So this table here that shows the observed and the expected, when you get into your first calculations of a chi-squared score, you're going to want to make sure that you have these available, because the next quantity is going to involve both of these values. So if we take a look at the observed versus the expected in a bar graph, what we can see pretty clear is that there are some differences. If we take a look at the expected value of blue versus the observed value of blue, we can see that there's an obvious difference. But we can also see that for orange, yellow, and the others, they'd have differences, but I think we all know by now that we don't split hairs in statistics. If we're talking about plus or minus 1 or 2, then chances are statistically that's not going to be significant. But these colors of blue and yellow especially, those are colors of some interest. The chi-squared is going to take these ideas into consideration when we do this test, so you don't have to necessarily pick the right one. If we were doing a one proportion test and we picked a color like green, we might statistically find out that there is no difference in green, so therefore we're making the claim that the factory is giving the product that we want. But with the chi-squared, it tests all of these proportions simultaneously and gives us the statistical value that we can then interpret of whether the factory is giving us the product that they expect or not. So this is the calculation for the chi-squared statistic. So it's just the same idea as when we calculated the Z statistic or the T statistic. This is the point statistic that we are going to use. And it's the sum of all of the differences between the observed and expected squared divided by the expected value. And so we are actually going to perform this calculation for each of the proportions, which is why it's important to calculate the expected values for all of the colors or all of the different quantities in your categorical data. And then we're going to calculate this chi-squared score based upon all of these. So this is a table now that is showing you how you would do that. We would take the observed blue minus the expected blue, square it, and divide it by the expected value, plus, and continue through the various colors. So you can see that if we're doing this by hand, this is going to be quite the taxing calculation, because in this case we have 6 proportions, but imagine that we have 18 proportions. You're not going to want to necessarily do that by hand. But again, when we're dealing with accessible type work, it's always important to demonstrate that you actually understand how to calculate this chi-squared by hand. But most of the time we're going to go ahead and use some sort of technology to aid us in this. One of the benefits to doing it by hand, however, is in a future lesson we're going to talk about how we can pinpoint specific quantities within that chi-squared score that added more to the overall score than others, and that's another piece of analysis that we can do. And so when we take a look at this, we get a chi-squared score of 10.18. Don't be shocked when you see chi-squared scores that are quite large. This is a pretty standard practice. And the thing that I want to point out as well is when we talked about it initially, we said that, well, blue and yellow were showing a pretty large difference compared to the other colors. And you can see with the chi-squared score, those two colors are actually adding a little more to the overall score of 10.18 than the others. This is the type of analysis you can do once you have all of these chi-squared scores for each proportion calculated. So this is the chi-squared score, and from here, the process is going to be very much the same as all significance testing you've dealt with before. So with knowledge of how to calculate the chi-squared score, we can begin to talk about how you would actually set up the significance test to come up with meaningful statistical conclusions. Well, we know state plan do conclude is going to be the essence of this, and with this distribution, we're going to deal with the conditions very much like we dealt with them with the t distribution, because we have a degrees of freedom that has to be calculated. So degrees of freedom when we're talking about the chi-square distribution is actually the number of categories minus 1. So don't take the sample size of 60 minus 1 in this case. We had 6 categories for the M&Ms, which means our degrees of freedom in that case would be 5. You can see if we take a look in the bottom right corner here that the shape, very much like the t distribution, will change according to the number of degrees of freedom. You can see that as we increase the degrees of freedom, we get this more stretched out flat chi-squared distribution as opposed to smaller numbers. Another thing that's important with the conditions in this case is instead of a large counts scenario, we're going to deal with the expected counts, and all of the expected counts have to be at least 5. Keep in mind that we are talking about the calculated counts, not the observed counts. So even though we have an observed count and maybe there's values less than 5, when we actually do the calculated expected values using the given proportions, we should end up with all at least 5. So if we take a look at actually finding a p-value from a chi-squared distribution, once we've indicated which distribution we're dealing with based upon the degrees of freedom, we can take a table, for example, and we can find out that in this case, our chi-squared score is going to be in between a p-value of 0.05 and 0.1, which means that we don't have sufficient evidence to reject the null hypothesis. I want you to also notice that in this case, we are dealing with the upper tail probability alone. There is no such thing as a two-sided test with a chi-squared distribution. You're always going to have your chi-squared score and determine the probability of the value being farther away than that. So make sure that you recognize that we're always dealing with the upper tail probability in this case. But the conclusions that we make based upon the p-value are exactly the same type of conclusions that we do when we're dealing with any other type of significance test. So we can begin to summarize the chi-squared test very much like we did with the other tests. And we've already dealt with the state part of this. And with the conditions, 2 of the conditions are the ones that we always deal with. If it's not randomly selected or randomly assigned, then we're going to have a huge amount of bias associated with it, and we're not going to be able to believe in the results that we get statistically. The 10% condition, of course, is essential in this because we're dealing with proportions, and so if we mess with the independence of these proportions and the population, we're going to have an issue overall with the statistical validity. With the large counts this time, we're dealing with the expected counts instead of the previous calculations we've done. So in this case, all of the expected counts have to be greater than 5. Again, it's not the observed, it's the expected. I would show this comparison directly, not just state that yes, all expected counts are greater than 5. I would flat out show that 14.4 is greater than 5 and do that with all the other particular expected counts. So if we take a look at this from the large picture, we can see that we have a script for the hypotheses. We find the chi-squared score, and from that we can begin to determine the p-value and the overall conclusions that we can make with that p-value. So state, plan, do, conclude is very much the case. It's very similar to a t-distribution in that we have degrees of freedom that we have to deal with. We have conditions that we've talked about already. And so again, by this point in your statistics career, hopefully the chi-squared goodness of fit test is not a big extension from anything else that you've learned previously. So if we do an example problem to end this lesson, we're going to deal with hockey players' birth months as an influence on their chances of making it to the NHL. And so the test that we want to do is to see if the birth date is related to this overall result. We're going to take a random sample of 80 NHL players and determine what their birthdays are and record them. So the first thing we have to do, of course, is come up with a one-way table for these 80 players. And we've done this according to January to March, April to June, July to September, and October to December. And you can see that we've sorted it according to the data that we're given. So the state now is going to be our null hypothesis. And in this case, we're going to say that the birthdays of the NHL players are evenly distributed among the 4 quarters. Keep in mind that they didn't state any proportions, but the idea being that the quarters of the year are all the same proportion. It's 0.25. Well, because this is a chi-squared test, the alternate would be that they're not evenly distributed, that at least one of the proportions is going to be different. And because there's no significance level given, we're going to go ahead and use alpha equal to 0.05. This is a great rule of thumb that you should do in almost every single case. So when we do the plan, we're going to check for random. We said that it was randomly sampled, which is good. The 10%, we're going to go ahead and say that 80 players sampled ends up being 800 NHL players in a population. We're pretty confident that there's at least 800 NHL players in the league, which means that we satisfy this 10% condition. When it comes to large counts, you would have to calculate each of the expected values. Well, we had 80 observed NHL players, and if 0.25 is the proportion for each of the 4 quarters, then our expected counts for each of those quarters is going to be 20, which is certainly a value larger than 5, so we've satisfied the large count. So we have satisfied the conditions that allow us to perform the chi-squared goodness of fit test. Now let's do it. We're going to calculate the test statistic, and again, we take the observed minus the expected for each of the proportions and add them up, so we get a chi-squared score of 11.2. Again, we're not going to do this analysis now, but you'll notice that that first quarter of the year and the last quarter of the year provides significantly more to the overall chi-squared score. That's interesting, being that those particular quarters also encapsulate the winter months. And so if you do analysis beyond just the statistical analysis, that might be something of interest to the people doing this study. We now know that the degrees of freedom are going to be 4 categories minus 1, which is 3. We have our chi-squared distribution. We find our p-value from a table, and we know that it's between 0.01 and 0.02. Well, that's a very low p-value, which means that in this case, we reject the null hypothesis, and we have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. So this isn't a gut instinct idea. This isn't something that you just look at the values and say, oh yeah, it's pretty obvious. You do the statistical calculation, and based on the fact that we've performed a comparison of all the proportions together, we get this p-value that is exceptionally low that allows us to make the meaningful statistical conclusion that we can make. So that concludes our first lesson on the chi-squared distribution. You can see its usefulness when it comes to comparing observed proportions to expected proportions in a multiple proportion scenario. I highly encourage you to take a look at these in other aspects of science and math, because this is a test that comes up a whole bunch. Good luck with your practice problems, and we'll see you again.